Uh, so as Agnita said, I will today be presenting on energy balances. So essentially, over the last 3 days, you've had presentation from my colleagues on the 5 different fuels, so natural gas, oil, coal, renewables, and electricity. And so energy balances essentially take all those 5 fuels and put them together. So that's what I will be presenting today. So first I'll be presenting what is an energy balance. Then I'll present why we create an energy balance. Next, how energy balances are calculated. Then I'll discuss a bit the IEA energy balance layout, and then followed by uses of energy balances. So first, let's have Menti. Is your country producing a national energy balance? So you can see the code at the top of the screen. So I see that many of you are producing a national energy balance. That's great to hear. So I hope this presentation gives you some more information on potentially how that energy balance could be improved or utilized. So first, let's discuss what is an energy balance. So energy balances are a compact way of sharing information on a national energy system. So according to the international recommendations on energy statistics, they are an accounting framework for compilation of data on all energy products entering, exiting, and used within the national territory of a given country during a reference period. So energy balances essentially summarize the entire national energy system of a country. So let's look at the different components of an energy balance. So on the rows, we have the different energy flows listed. Sorry, Audrey, I think one of the IEA channels isn't muted. So on the flows of the so on the rows of the energy balance, we have the different energy flows. So on the top, we have supply. So this summarizes all the energy coming in and out of the country, and this is summarized as total energy supply. So total energy supply is a very important indicator, and it is essentially summarizes the energy available for domestic consumption within a country. Then we have the transformation sector and energy industry own use. So this part of the energy balance captures the transformation of from one energy product to another. So for instance, from coal to electricity. And then finally, we have final consumption. So this captures how energy is finally consumed within a country. So another important component of the energy balance is we have all the different products, and this is key. It's comparable information for all products. So in order to compare products, we need to first convert them into comparable energy units. So in your statistics, we will have, for instance, coal collected in kilotons, and we'll have electricity collected in gigawatt hours. But for an energy balance, we need, in order to compare these products and also summarize it in a total, we need to convert them to energy units and all the same energy units. So now, once they're in the same unit, we are able to compare products. So that is one of the main advantages of an energy balance. And finally, so because of these features, it's able to give a global picture of energy situation in a country, both how all the products and how they are supplied and consumed. So you may be familiar with Sankey diagrams. So Sankey diagrams are essentially the energy balance reversed. So instead of having the energy flows on the rows and the products in the column, now you have the products in the rows and the flows going across horizontally the screen. So this is a very useful way of visualizing an energy balance. But of course, in order to get this product output, you first need the energy balance in its matrix form. So now that I've given a brief introduction to energy balances, we'll talk about why do we create them. So there's multiple reasons, And as I said, its main function is we're able to compute and monitor the total energy supply and consumption, as well as patterns for the whole energy market. So again, we're able to look at how different products are consumed all together, and maybe see, for instance, if one sector is transitioning from one fuel to another. So this information could be shown in an energy balance. It also allows us to look at the relative weights of different energy sources in the total energy mix. So for instance, if your country wishes to compute the share of renewable energy in your total energy supply, you would need an energy balance to do that. You're also able to compare consumption shares across sectors of economic activity, and compute indicators such as energy intensity, dependence on energy imports, and other socioeconomic indicators. And then finally, energy balances allow you to look at similarities or differences with other countries' energy systems. So if countries have the same format of energy statistics in the form of energy balance, then this allows you to compare with different countries and also compute regions such as the world energy balance, because countries' energy balance can be on comparable terms. And then finally, energy balance can also be a useful tool for looking at data quality. So for instance, you can use it to calculate statistical differences and the efficiency in the transformation sector that can give you an idea of the quality of the energy data. So now let's discuss how energy balances are calculated. So as I said before, my colleagues have discussed how you can collect statistics for each of the 5 fuels. So once for the individual fuels, the statistics are collected either through questionnaires or other means, we can compile these into a commodity statistic. So this is also called a commodity balance, and these may have products in different units. So once we have the commodity statistics, then we can go to an energy balance by converting all the units to the same energy unit. So now let's do a quick Menti. So in order to convert mass, which is the commodity, the different units of the commodity statistics, to energy units, which is the units of the energy balance, what do we need? So the options here are density, calorific value, and carbon content. You can see the Menti code is at the top of the screen, just 87764577. So yes, I see all of you have got it. That's excellent. It is indeed the calorific value. So the calorific value, just to reiterate what was said in the prior presentations, is typically in units of energy per mass. And so once you have statistics by product, then you have your calorific values, which you can multiply by your statistics by product. Then we do a quick format change, which I'll discuss in more detail later. And then from there, you get your energy balance. So just to reiterate, a calorific value is the amount of heat obtained from 1 unit of mass or volume of the fuel, and is the only way to convert a fuel quantity from physical units to energy units. So when we're talking about creating an energy balance, calorific values are very important in this process. And not only are having calorific values important, but also the quality of the calorific values are important. So I'll just give a brief example here. So here we have a commodity balance with bituminous coal in kilotons, and we can see that the statistical differences are 0. And then we have a table of net calorific values for each of the various energy flows, also for bituminous coal. And then when we apply these calorific values, we have our energy balance. However, now you may notice in the energy balance, we have statistical differences. So where did these come from? Well, if you look closely at the net calorific values, you can see that on the supply side, all the net calorific values are higher than the calorific values on the demand side. So there's a mismatch here, and this is creating your statistical differences. So a statistician might have to look at this and go back to different data suppliers and investigate the calorific values here to see if maybe on the supply side they're reported too high or the demand side is reported too low. So again, you need to collect to create a good energy balance, both good quality data for physical quantities as well as calorific values. So now I'll discuss some energy balance methodological choices. So things to consider when you're defining the format of your energy balance. And then, of course, I'll also get into what the IEA has chosen for our energy balances based on the international recommendations for energy statistics. So first, you need a common unit of account. We need to decide on the net versus gross calorific value approach. We need to look at calorific values by product. We also need to look at primary energy form for energy transformations that do not involve combustion. And then finally, how we calculate the primary energy equivalent. So first, let's look at which energy unit. So truly, it doesn't matter which energy unit you choose, although some may be easier to understand and than others. So the IEA has chosen joules for our energy unit and the energy balance. But the main thing is that regardless of what energy unit you choose, it should be the same across the entire energy balance and very clearly defined. That is the most important consideration. So now let's look at net versus gross calorific values. So just a reminder, the difference between the net calorific value and the gross calorific value is the latent heat of vaporization of the water produced during combustion. So essentially, the net calorific value is represents the useful amount of energy content of a fuel because this heat in vaporization is lost unless you have condensers. So that's why the IEA has chosen to represent our energy balances on a net calorific value basis, because that's the quantity of usable energy. So this means that when calculating an energy balance, you need to make sure that all fuels are not only in energy units, but in energy units on a net calorific value basis. So the biggest example of this is natural gas, which in the commodity statistics is reported in terajoules gross. But so we need to convert this to a net calorific value basis by applying the standard 90% conversion. So we also need a choice of calorific values by product. So calorific values can vary over time between commodities, from country to country, and from flow to flow. So ideally, you want the calorific values to be reported on a very granular basis. So for as much detail as possible in terms of the different products and the different flows. And indeed, the IEA is currently doing this. We have different calorific values on flow, depending on the flow, as specifically my colleagues who presented coal discussed. So next, this is a very key methodological point for energy balances. So how do we determine primary equivalents for non-combustible sources? So combustible sources have measurable inputs in the context of transformation. So for instance, if we have natural gas being transformed to electricity, we can measure the electricity output from that plant, and we can also measure the natural gas input to that plant. So we have two measured values, and it's easy to represent this in our energy balance in the electricity plant input and output. But what do we do in the case of non-combustible sources like nuclear, geothermal, solar, wind, wave, and hydro? So we have the output is clear. So for instance, we know the electricity output from a hydroelectric plant, but how much is the related amount of primary energy? So how do we express the input of this transformation process? So in order to define the input, we first need to identify what is the primary energy form for non-combustible sources. So we need to consider and define the primary form of energy to be considered in the supply part for the following sources. And that's nuclear electricity, geothermal, solar thermal, hydro, wind, wave, and solar photovoltaics. And so the IEA has chosen to define the primary energy form as the first energy form downstream for which multiple energy uses are practical. So let's just discuss with a quick example. So for instance, for wind, we know that output is the form of electricity. So what is the first useful form of energy from this transformation process? Well, technically, we could measure the kinetic energy from the wind that's blowing, but that's not a useful form of energy, really. So the first useful energy form in this process is the electricity from the turbines. So it just so happens that electricity is both the output and the input in this definition of this system. So let's give another example looking at a case where the primary energy form is heat. So for nuclear, we have electricity output from a nuclear plant. So we know the output. Then in order to define the input, what is the first useful form of energy in the system? Well, we could say is from the energy contained in the nuclear fuel, but that's not really useful form of energy until it goes through the transformation. So the first useful form of energy in this case is the heat produced from the reactors. So our primary energy form is heat, even though our form of output is electricity. So now that we've defined the primary energy form, we need to calculate the primary energy equivalent. So essentially, we need to quantify the primary energy form, and we call this quantified value the primary energy equivalent. So in order to quantify the primary energy form, the IEA has opted for the physical energy content method. And this simply refers to the fact that once we've chosen the primary energy form, in order to calculate the primary energy equivalent, we just calculate the physical energy content of that primary energy form. So because of this, we have these implied efficiencies when we go from output to input, and the implied efficiencies for the various products are shown below. And so this is something that maybe you just have to remember when you're creating an energy balance or have as a reference. So just to give an explanation, let's take the example of hydro. So you have your output of hydroelectric transformation is electricity. So you have electricity output. And the first usable form of energy, your primary energy form, is also electricity output from the turbines. So in order to convert from electricity to electricity, it's 100% efficiency because there's no losses there. You're going from electricity to electricity. So that's where we get that 100% implied efficiency. Whereas if you're going from, let's say, electricity to heat, as in the case of nuclear, then we need to define what these efficiencies are because it's a transformation process. Some energy will be lost. So we've defined that efficiency as 33% for nuclear. And this number came from the average efficiency of nuclear plants across Europe. So it's predefined. So if you have the electricity output from a nuclear plant, then you would have to apply a 33% efficiency to calculate the input in heat form. So I mentioned hydro is 100%, also wind and solar, 100% implied efficiencies. Nuclear is 33%. Geothermal, which the primary energy form is heat, is 10% implied efficiency for electricity generation and 50% for heat generation. And then solar thermal heat is 33% for electricity generation and 100% for heat generation. So we're going to do another Menti. So I just want to reiterate that for solar thermal, which has heat as a primary energy form, that implied efficiency to electricity generation is 33%. So we can look at the different conversions here, and you can see how once we have the electricity output in a certain form, we can use the implied efficiencies to back calculate the inputs to the system. So taking a look at nuclear, as I explained before, you have 1,000 terajoules electricity as your output. You use the 30% efficiency to get your primary energy equivalent, which is heat. And in this case, it would be 3,030 terajoules of nuclear heat. So to summarize, primary energy equivalence is equal to your energy outputs divided by your implied efficiencies. So let's do a quick Menti. So what is the primary energy equivalent for solar thermal with 1,000 terajoules of electricity produced? Okay, so I see have some of you've got it. So indeed, the correct answer here is 3,030 terajoules. So the reason why it's not 1,000 is because you have solar thermal heat is your uh, primary energy form, and then you have 1,000 terajoules of electricity produced. So you need to go from electricity as your output to heat as your input. And so that is a 33% efficiency. So we'll look at this concept more in the exercises. So I want to quickly look at also the IEA energy balance layout. So I already discussed some key structural features of an energy balance, including the 3 different sections: supply, transformation, and final consumption. But one important thing to note about the supply side is that you'll notice that for oil products and electricity, we have 0 in the production row in supply. So why is that? Well, it's because oil products and electricity are actually secondary products. So they are output from transformation, and therefore their output is represented in the transformation sector as opposed to the supply side, because it's not truly a primary energy form, it's a secondary energy product. So, and this is also to avoid double counting so that your total energy supply is representative of your primary energy within a country. So now let's look at the transformation sector. So an important concept here is in the transformation sector, negative values represent an input and positive values represent an output of a transformation process. So for example, let's look at the crude oil column and the oil products column in the oil refinery row. So we can see there's a negative value in crude oil column and oil refinery row, and this represents crude oil input to refineries. And then you'll see beside it, we have a positive value in the oil products column in the oil refinery row, and this represents output of a transformation process, so oil products output from refinery. And then if you follow the row across to the total column, you'll see in the total column, we get our transformation losses, since the total is the sum of all the products. So transformation losses should always appear negative, of course, because we can't have any energy gains in a transformation process. So they should always appear negative in the total row. And if you have any positive transformation losses in the total column, then that would be an indication that maybe there's something wrong with the efficiencies of your transformation. So very quickly, we'll go over the uses of energy balances. So energy balances can be combined with socioeconomic indicators. to produce useful indicators to represent a picture of the country. So we'll look at some important ones now. So for instance, we can use the total energy supply from the energy balance and combine it with population to calculate TES per capita, which can maybe represent many factors contribute to TES per capita, but it can potentially represent, for instance, increasing access to energy and improving quality of life for households in a country. We can also calculate TES over GDP, which is also known as energy intensity, and it represents how efficiently a country can generate wealth from energy. So we can see per unit of GDP how much energy is required to create that wealth. So ideally, a country would want lower value, and that indicates that they're efficiently generating wealth with their energy resources. Another important indicator is self-sufficiency. So this is calculated as production over total energy supply, and it indicates if a country is able to meet its own demand, energy demand domestically. So if a country is able to produce what it demands, so if this indicator is over 100%, then that means that yes, they're able to meet their own energy demands for that product. And if it's under 100%, then that means they have to use imports to meet their energy demand. So finally, energy balances can also be used to calculate CO2 emissions, which we won't discuss here, but of course are very important in terms of tracking climate goals. And energy balances are also used in the calculation of some of the sustainable development goals, such as the share of renewable energy in a country's energy supply. So to summarize, good energy balances require good quality statistics, including both good statistics for physical data and calorific values. They are a compact source of energy information. They enable accurate checks of energy statistics, but for instance, by looking at efficiencies and the transformation sector, and they constitute the foundation for basic energy indicators, energy accounts, and for CO2 emissions estimates. So we have lots of resources online, including energy balances if you are interested in exploring our data. And of course, as you've seen in other presentations, resources for statisticians that also provide info on some of these concepts I discussed today. So thank you very much. Are there any questions?